So now that we've learned all about the different types of circuits, series and parallel circuits, and what exactly a circuit is and some of the basics behind circuits, we're now going to focus on how to do some calculations related to circuits. For starters, we've already talked about how current and resistance are inversely related. So as resistance increases, current decreases and vice versa. It can also be shown that current and voltage are directly related. This should make some sense when we know that voltage is about how much energy a circuit has. If you have more energy, those electrons are going to move faster. So this is a pretty logical conclusion based on what we already know about energy and movement. So what I want you to do is try and pause this video real quick and see if you can write a single equation that summarizes these two relationships. Once you're done with that equation, unpause the video and see how your equation that you wrote compares with the true equation. So here's the equation that summarizes these two relationships. Current is equal to voltage divided by resistance. This is known as Ohm's law, which is named after a German physicist, George Ohm, who wrote about his discovery with these relationships and came up with this equation in 1827. We commonly write this in a slightly different order, though. Rather than I equals V over R, this is commonly written as V equals IR, or sometimes you might see it as delta V equals IR. This comes from the fact that V or delta V are both symbols that can sometimes be used for voltage. We'll use this equation quite a bit in this class. It's probably one of the most important circuit equations that we have, and so you'll probably have this one memorized by the time we're done with this unit. Now, another equation, another quantity that we often calculate in circuits is power. And we learned in a previous video exactly what power is, the rate at which energy is dissipated or transformed into another type, but we didn't learn any equation for power. So one way of calculating power is that power is current times voltage. This is the equation that'll be given to you for any assessment that you have. However, when we are talking about power, you can write it in two other ways using Ohm's law. So if I use Ohm's law in that I equals V over R way, and I plug that in for I in my power equation, I can find that power is V squared over R. Or if I plug in V equals IR into the V in the power equation, I could write power as I squared R. These two other formats for the power equation will not be given to you, so you'll need to be able to derive them. But they can sometimes be useful when we are reasoning about the power of something, or in some cases when we're reasoning about like the brightness of a light bulb, since the brightness of a light bulb relates to power. The light bulb itself wouldn't change resistance, and so its power can be directly related to the current that's traveling through it or directly related to the voltage. Now, one other tool that we will use in analyzing circuits mathematically is something called a VIR chart. And a VIR chart is simply a method for kind of organizing the values that we commonly have in circuits. So those values being voltage, current, and resistance. So I'm going to explain a VIR chart with an example here. So for starters, we'll do a VIR chart by writing out VIR. And the first thing we're going to put in our VIR chart is the value of each resistance in our circuit. So this example circuit has 3 resistances. It has a 3 kilo ohm resistor, a 10 kilo ohm resistor, and a 5 kilo ohm resistor. And then once we write all those resistances, we're going to put a horizontal line in here. Our last row in our VIR chart is going to be for our totals for our circuit. For voltage, the total is going to be the voltage of your battery, which is given to us as 9 volts. And because this is a series circuit, I know that I can add those 3 resistances to get the equivalent resistance for the series circuit. So 3 plus 10 plus 5 gives me 18 kilo ohms. It's totally fine for you to leave this in kilo ohms in my chart. However, when we're doing calculations, you need to make sure you're converting to ohms, since that's the standard unit for resistance. So now we want to fill out the rest, because my goal here is going to be to find the voltage and the current for each resistor, as well as the current that's traveling through the battery. In order to do so, I'm going to be using Ohm's law, V equals IR. I'm going to start using Ohm's law to find the current in the battery. So this value that's missing right here. So I'm going to use 9 volts as the voltage, and I'm going to use 18 kiloohms as the resistance. Again, paying attention to the fact that I need to convert 18 kiloohms to ohms, which would be 18,000 ohms. And so when I plug that into my calculator, I get a pretty small number when I do 9 divided by 18,000. I end up getting 0.00005, right? So we don't want to put all those zeros in there. That means you could either choose to put this in scientific notation. So in scientific notation, this would be 5 times 10 to the negative 5th amps. Or I could convert that into milliamps. And if I had that in milliamps, I would plug in 0.05 milliamps. I totally made a mistake there. I apologize. When I plugged it in my calculator, I had one too many zeros on my 18. So this should be 0.5 milliamps, or 5 times 10 to the negative 4th amps. Either one of those is totally fine for you to write in there. Now I have to go to what I've learned about a series circuit and the current and voltage in my resistors. So in a previous video, we learned that the current is constant in a series circuit, and that the voltage adds, so that the voltage of the battery is equal to V1 plus V2 plus V3. So since my current is constant, every single value of I is going to be the same. So either 5 times 10 to the negative 4th amps or 0.5 milliamps. The nice thing about VIR charts is once you've filled out 2 of the quantities in a given row, you can always find the third using Ohm's law. So now that I know the current and resistance of each resistor, I can find the voltage by multiplying those 2 quantities times each other. So that 0.5 milliamps times 3 kiloohms, again, paying attention to those prefixes as we're doing that multiplication, this will end up getting me 1.5 volts. That 0.5 milliamps times the 10 kiloohms will give me 5 volts. And that 0.5 milliamps times 5 kiloohms will give me 2.5 volts. It's always a good idea to check your math here. That's pretty simple to do, because if I add together these 3 quantities, I should end up with 9 volts, since the voltage of the battery is the sum of those individual voltages. And luckily in this case, that does work out to be so. So one thing you'll notice is that every time I used this equation V equals IR, I did not write out my work for that equation. We'll use this equation so many times in analyzing a circuit that this is one of the few times that I give you a pass in writing out your work. You do not need to write it out if you don't have to. Now, if it helps you to write it out, you're welcome to do so. One thing that I am requiring you to do is to arrange your answers in this VIR chart, because it makes it way easier for me to check answers and check work as I'm checking your work on any assessments. Obviously, I went through this example with a series circuit. The work would look different if you had a parallel circuit instead, where the voltage is the same for every resistor and the current adds up. And so if that were the case, whatever the voltage of the battery is the number that you're going to fill out for the voltage of each resistor, and then you'll use V equals IR to calculate the current. What we'll see later on in class is that we have some combination circuits where there's a combination of series and parallel, and in that case, these V equals I charts are going to be crucial in analyzing our circuits.